Welcome to this short tutorial which is going to look at coordinate systems and using 3D shading in Houdini. First of all, quick recap on what coordinate systems are. Well, we all know from very basic mathematics that any point in space can be represented using three coordinates in the x, y and z direction. Unlike other 3D applications, Houdini has default coordinate system called the world coordinate system, which is what we see represented here by the three coordinate system markers and the grid. What happens if I lay down an object? Let's lay down a box and dive inside, and I can see that I have some size parameters and a center, and these are obviously points expressed in a coordinate system. And at the moment, the center of the box is at the center of the world coordinate system, the origin of the world coordinate system. But what happens if I go up and, let's say, rotate the box and move it? Now, if we go inside the box, we can see that the center of this SOP is still described as being at 0, 0, 0. So it's at the origin of some coordinate system, but clearly it's not at the origin of the world coordinate system. So what we've in fact got here is two different coordinate systems. There's one in which this box is being constructed, where the origin is at the center of the box. And there's another one here at the scene level, which is the world coordinate system, where the box is in a different place. So whenever you describe a point, the three coordinates of a point, you have to know which coordinate system you're expressing them in. The three coordinates 0, 0, 0 here, expressed in the coordinate system in which this box is being constructed, mean a point in the world coordinate system which is clearly not at 0, 0, 0. If I lay down another object, say a torus, and again if I lift it up and rotate it, the same thing is true. We've got another coordinate system here whose origin is at the center of the torus. So for almost every object in the scene you're going to have a different coordinate system. In Houdini, coordinate systems are sometimes also called spaces, and so this is world space, the default coordinate system, and inside here we have what's called an object space, and it's particular to this object and is determined by the transformations. And we have another separate object space here for the torus. There's another very important coordinate system, which is the one that's used when mantra is rendering, and I'm going to lay down a camera so that we can have a look at that. And let's zoom out. Here's our camera, and as it happens, the camera manipulators correspond to the axes of the camera coordinate system. The green axis here represents the y direction of a camera coordinate system. The red axis here represents the x direction, and most importantly, the camera is looking down the z axis. And obviously the origin of the coordinate system is at the lens of the camera. So if we were looking at these objects from the point of view of the camera coordinate system, they would have quite a large z value because they're a long way from the camera. There's one other coordinate system which I'll cover when we get into shading, but knowing which coordinate system your points are in is very important for successful shading in Houdini. So to look at how these are used in shading, let's delete our torus, and I'm going to go to the material palette and I'm going to lay down a basic surface, and we're going to use this as the starting point for a bespoke shader. So I've dived down inside and I'm going to alter the surface color, and I'm going to do that by feeding a different value into the base color of this node here, and that means that our shader will create the surface color based on whatever we feed in here. And I'm going to use a turbulent noise node, and I'm going to lay down a global variables node. I'm going to output a single variable, which is the surface position, and I'm going to feed that into the position of our turbulent noise. And I'm going to leave the values as they were, and I'm going to put down a color mix SOP like so, and I'm going to leave this at the default, and then I'm going to take the output of this and feed it in to the base color. So what we're doing is shading our object based on a noise value driven by the position of the point that we're shading, not the position of the object, but the position of the particular point that we're shading. Let's have a look and see what that looks like. And let's have a look through our camera. And I'm going to zoom in so that we can see things a little bit better. And I'm going to also need to set up a light, because I haven't yet done that. So we'll set up a distant light. And let's try rendering and create a render node, and let's try rendering that. And of course it would help if I'd applied the shader to my object. And there we have it. Well, we can see the color is varying nicely in a kind of noisy way. Let's make it a bit more pronounced. And I'm going to do that by changing the parameters of our color mix node. And let's go for some things that are rather more contrasting. So I'm going to reduce this and increase this so that we have a more deeper contrast. And the other thing I'm going to do is increase the frequency of the noise. And let's take another render of that. Now we see we're getting a much more complicated pattern of noise. But let's look and see what happens now if we animate our object. And I've skipped ahead and put some simple keyframe animation on our cube, and I've rendered out the first 24 frames here into mplay. And if we go through these, we can see that our texture is changing at every frame. Now that may be what you want, but it's very rarely what you actually want. So how can we prevent the texture changing at each frame? Well, it's actually pretty simple. The reason that the texture is changing at every frame, the shading is changing at every frame, is because we're taking a position value for the particular point we're shading, feeding it directly into our noise. Now that position point, say this corner of the box, is by default in the shading context here measured in camera coordinates. And obviously, since we're looking through the camera here and the box is moving, the coordinates of this point will change over time. And so, because the coordinates are being fed directly into the noise calculation, the result of the noise calculation, and thus the color, will change at every frame. Now one way to prevent this is to transform our position into a coordinate system which stays tied to the object. And the way to do this is using a transform VOP node. And as you can see, it has a entry for the vector that we're going to transform, and then it has parameters for the space that we're transforming from and the space that we're transforming to. And by default this takes the current space, which is fine in this case, and transforms it to the object space. There are other options here. There's world space, but it would be no good transforming these coordinates into world space because we'd have the same problem. The points on the cube would change in world space at every frame. We can transform them into camera space, but that's the space that they're already in. We can transform them into object space, which is what we're going to do, to something called texture space, which in almost all circumstances, for Mantra at least, is the same as object space, and finally into something called NDC space, which we'll come on to later. So what happens if we do this transformation? And by the way, when you do transform a point or a vector, it's important to make sure you set this interpretation drop-down box correctly. As you can see, it has three settings: one for position, which is what we're doing here, one for a normal direction vector, that is a vector that's been calculated by subtracting one position from another, or for a normal. So we'll stick to position, and let's feed this in to my position, and now I'm going to re-render and let you see the result. Well, now we can see that as we scrub through our animation, the texture is no longer changing between frames, but is stuck to the object. Well, let's look at a different problem now, which has a different solution. What happens if I'm actually transforming the points of my object relative to each other? In other words, having animation that's not going on here at the scene level, but inside by transforming some of the points of the box relative to others. So let's just delete the animation that we've got here. I'm going to go down inside. I'm going to hit S and 4 for primitives. I'm going to select the top of the box, and I'm then going to lay down a transform node. And this is going to transform the top of the box. And I'm going to translate it by, say, $f times 0.5. So this means as the frame number increases, in fact let's make it times 0.1. As the frame number increases, the box is stretched, like so. Well, let's see how that looks if we render it. Render. And we can see, unfortunately, the problem of the texture changing with every frame has returned. And it's pretty simple to understand why that's happening. If we look at our shader, we're bringing in still a point and we're transforming it into the object coordinate system. Now the object coordinate system is no longer changing from frame to frame because I took away that animation at the scene level. Instead we've got some animation that's changing the position of points within the object coordinate system. So for those points, this value of noise is going to change at every frame, and so our pattern is going to change. But there is a way around this problem too, and it's a good thing that there is, because it's a very common issue with, for example, animated characters. Your character's musculature will move with every frame, and if you want to use a noise function to texture shade your character, you're going to need to find a way around that problem. And the way around it is to make a change in your model, which I'm going to do here, and you must make that change before you apply the animated transformations. And the change is to add a rest position SOP. And what this does is create some, and we can look at this in the details view, create a duplicate of your position coordinates taken at a snapshot at this particular point in the network. So here we can see that these values of position and the values of rest are the same. If we now have a look at our final node and move the animation on, we can see that the values of position are changing, but the values of the rest coordinates are not. So what this does is record the positions of the points that make up our geometry at a certain point in the network which is not animated. And that means that we can use these points, the rest points, as the points that determine our shading, rather than the actual points of the object which are being animated over time. And it's quite simple to change our shader to do that. Let me dive inside here, and we can get rid of the global position and the transform, and instead we need to bring in a rest position VOP, and this is going to produce in camera coordinate space a set of positions which we can use to drive our turbulence and thus our colour. And again, let's render this out and see what it looks like. Here's the result of that render, and if we scrub through we can see that what happens now is our texture is stretched along the side of the box, as for example we might expect to happen to a pattern on our character's clothes when they were moving. So that's how to use rest coordinates to ensure that your pattern does not change from frame to frame in an unwelcome way. I should correct something that I said slightly earlier on in this video. The rest position VOP in fact produces some coordinates in texture space by default. Now that may occasionally matter, and you can change the space in which the coordinates are produced here, but in fact any coordinates which do not vary with time are good for driving the turbulent noise function. Finally, at NDC coordinates. Now NDC stands for Normalized Device Coordinates. And what this means is that it's a coordinate system relative to the device that you're using to view your scene. So in this case it's relative to the camera, and it's different from camera coordinates because of the way the X and Y coordinates are measured. In NDC coordinates, the X and Y coordinates of a point always vary between 0 and 1, providing the point is visible within the camera's viewing frame. Now points on objects that were down here would have X and Y values close to 0 and 0 for the X and Y components. Points on objects that were up here would have X and Y components that were nearer 1. Let's have a look at the way this would work in our shader. So I'm going to lay down global variables again, output the position, lay down a transform node, feed the position into our transform node, and we're going to transform from current space into NDC space. And I've deleted the turbulent noise, and instead of turbulent noise I'm going to use one of the two-dimensional patterns. Let's use boxes, and I'm going to feed, let's enlarge this, I'm going to feed these NDC coordinates, the X and Y NDC coordinates, into the S and T coordinates for the boxes. So I need to convert my vector to floats, and I'm going to feed the X value into S and the T value, sorry, the X value into S and the Y value into T, and then we're going to take the amount and we're going to feed that into our color mix. And let's have a look and see what that looks like when we render. Let's in fact change the frequency of our boxes so that we can see a few more of them. and I'm going to increase the frequency to, say, 5. Well, 18 will do, and 18. And as you can see, what's happening with the normalized device coordinates is that the pattern doesn't appear to be related to the object, but appears to be a flat plane laid across the camera with the regular pattern. And that's because the x and y coordinates that we're getting here are relative to this viewing frame. Note that the z coordinate still relates to depth, but you very rarely want to use it when you're using NDC coordinates. So that's a brief introduction to coordinate systems in Houdini and how to use three-dimensional procedural textures in a way which ensures that they stick to objects when they move or deform.